Lesson 6E, Horizontal Projectile Problem Solving. Example number 1. A cannon is fired horizontally from atop a cliff 45 meters high with an initial velocity of plus 63 meters per second. Here is a sketch of the cannon and the estimated path of the ball and the height of the cliff as vertical displacement of negative 45 meters. The initial velocity is 63 meters per second forwards or plus 63 meters per second. Now the important thing here to recognize is the initial velocity is only in the horizontal direction, or in the x-plane. We denote this initial velocity in the x-axis as v subscript xi, where x stands for x-axis and I stands for initial. Now the blast gave the cannon a horizontal velocity, but no vertical velocity. Its velocity is purely in the x-plane. The initial velocity in the y-plane, therefore, is 0. The v subscript yi is 0 meters per second. Remember Newton's first law states that an object in motion will stay in motion, or an object that is still will stay still unless an unequal force acts on it. So why doesn't the cannonball keep moving to the right at 63 meters per second? If we ignore air resistance, then there's gravity, negative 9.8 meters per second squared. The cannonball drops so that it speeds up 9.8 meters per second downwards per second of dropping. So after 1 second, its horizontal velocity is 63 meters per second. There's no force to slow it down if you ignore air resistance. And its vertical velocity now is negative 9.8 meters per second in the y. After 2 seconds, the velocity in the horizontal is still 63 meters per second, while the vertical velocity now becomes 2 times negative 9.8, which is negative 19.6 meters per second. After 3 seconds, the vertical velocity is still 63 meters per second, as there's no force acting on it to slow it down, but the vertical component will now be negative 29.4 meters per second. And if the ball would travel for 4 seconds, the x component would be 63 meters per second, while the y component would be negative 39.2 meters per second. Question number 1. How long does it take for the cannonball to strike the ground? Well, here are our values. Our initial velocity in the x is 63. Our initial velocity in the y is 0 meters per second. Our distance above the ground is 45 meters, so the displacement vertically is negative 45, and gravity is negative 9.8 meters per second squared. Which kinematic equation do we use? 1, 2, 3, or 4? We know that the object needs to drop a distance of 45 meters. We know that the initial velocity in the y-axis is 0 meters per second, and gravity accelerates falling objects at negative 9.8 meters per second squared in the y. Our best choice would be equation number 2, d equals vi t plus 1/2 at squared. So here's equation, sudden displacement, initial velocity, acceleration. Note how 0 times t makes 0. Negative 45 equals negative 4.9 t squared. Isolate t squared. T squared is 9.18. Root t squared, and time is 3.03 seconds. Question number 2, how far from the base of the cliff will the ball land? Here's our values, and we just calculated t at 3.03 seconds. Which kinematic equation shall we choose, 1, 2, 3, or 4? We are calculating horizontal displacement, so how far sideways it traveled from the edge of the cliff. So we will need initial horizontal velocity as well as final horizontal velocity, which is a constant at plus 63 meters per second, and the time it's in the air for, which we calculated as 3.03 seconds. We know the horizontal acceleration is 0 meters per second, so we can use formula 1, 2, or 3. Let's choose 1. d equals vxi plus vxf over 2 times t. Sub in v initial and v final and time. d equals 63 times 3.03. Distance equals 190.89 meters. So based on our calculation, the cannonball will land 190.89 meters away from the base of the cliff. Question number 3. What is the velocity of the cannonball as it strikes the ground? We are asking for this velocity represented by the red arrow, which will have magnitude and direction since its velocity. Well, here's our data, including horizontal displacement that we just calculated at 190.89 meters. We will solve this problem using 3 steps. First, we'll calculate velocity final in the vertical as it strikes the ground, since we know the velocity in the horizontal is a constant at 63. We'll use component addition to find the resultant velocity. Then we'll present our answer, including the magnitude and direction. Which kinematic equation shall we use, 1, 2, 3, or 4? We need to find final vertical velocity. We know the initial vertical velocity is 0. We know the travel time is 3.03 seconds, and we know the vertical displacement is negative 45 meters. Acceleration due to gravity is a constant at negative 9.8 meters per second squared. We can use any of the four kinematic equations. Let's use number 4. We haven't used it yet. We're going to calculate the final velocity in the y-plane using v final squared equals v initial squared plus 2ad. We're going to sub in our initial velocity of 0, gravity, and our height at negative 45. Vf squared equals 882. Our final velocity in the y is 29.69 meters per second downwards, or negative 29.69 meters per second. For those that are used to using the acceleration formula, we can also solve for this using a equals v over t. Isolating v as t times a, we can sub in t and a as 3.03 and negative 9.8. Delta v, change in velocity, is vf minus vi. Vi is 0. That gives us velocity final in the y as negative 29.69 meters per second. Looking at my final velocities in x and y as being positive x and negative y, I know that my resultant will be in quadrant 4. Here's my origin. I will sketch velocity final in the x as 63, and I'll include velocity final in the y as negative 29.69. Using Pythagorean's theorem, we can solve for the resultant velocity, Vf, as 69.65 meters per second. Since it's velocity, we'll have to include direction. Using the tangent ratio, we can find that theta is 25.2 degrees. Now if we draw a line parallel to Vxf, we can use the z law to indicate that theta here is 25.2 degrees as well. Now we'll present our answer with magnitude and direction. The final velocity of the cannonball as it strikes the ground is 69.65 meters per second, 25.2 degrees above the horizontal.